Welcome to the class. Dear students, today we are going to discuss basicity of amines, relative basicity of primary, secondary and tertiary amine, and also the reasoning for the differences of basicity of primary, secondary and tertiary amine. After that we will discuss on the effect of substituents on the basicity of amine. So let us start. Basicity of amines. Amines are basic in nature. Ammonia. Amines are actually derivatives of ammonia. If one H is replaced, that is if H hydrogen is replaced by alkyl groups, it will lead to amine. If one H is replaced, it will lead to primary amine. If 2H is replaced with alkyl group, it will lead to secondary, and if 3H is replaced, it will lead to a tertiary amine. So amines are actually derivatives of ammonia. If you look at these structures, all of these are having nitrogen, and nitrogen is having a lone pair of electron. It is because of this lone pair of electron that amines and ammonia are basic in nature. Let me illustrate the last point much clearly. What is the point? It is because of this lone pair of electron that ammonia and amines are basic in nature. Let me illustrate this point very clearly by allowing it to react it with water. You know the property of water. Water is a aprotic solvent. It acts as an acid when it encounters a base. So here the water should act as an acid if it is basic, right? So let us see what happens. I am dissolving ammonia in water. What happens? It acts as an acid. Okay. What is the net output? The product is ammonium ion and OH minus. Similarly, I have dissolved primary amine, secondary amine and tertiary amine in water, or I have reacted it with water. And what did I get? Yes, alkyl ammonium, dialkyl ammonium and trialkyl ammonium ion. That's another thing. The thing is you get OH minus here, right? So what is OH minus? What does OH minus signify? OH minus signifies that this ammonia, primary amine, secondary amine and tertiary amine is arrhenius base. What does it signify? It is arrhenius base. What is the definition of an arrhenius base? What is the definition? What is arrhenius base? Substances when dissolved in water, if it releases OH minus, then such a substance is referred to as an arrhenius base. What is arrhenius base? Compounds when dissolved in water, if it releases OH minus, then such a substance or compound is referred to as an arrhenius base. So ammonia and amines are arrhenius base because when they dissolve in water, they release OH minus. So number one point is proved. Number second point that I want to say here, why it is acting as arrhenius base, or why OH minus is released. Why is OH minus released? It is because proton has been abstracted from water. Look, proton has been abstracted from water by the lone pair of electron in the nitrogen atom. Correct? So that is why OH minus is released. So the ultimate responsibility is the lone pair of electron on the nitrogen atom. It is because of the presence of lone pair of electron on the nitrogen atom that H plus is abstracted from water and it acts as an arrhenius base, right? And what is the Lewis base? What is a Lewis base? Lewis bases are compounds that donate pair of electrons. Lewis base is a compound that donates a pair of electron. Is it donating a pair of electron? Are the ammonia or the aliphatic amines here, primary, secondary and tertiary, are they donating the pair of electron? Yes. So it is a Lewis base also. So by donating a pair of electron, amines are Lewis base. Correct? And by producing OH minus when dissolved in H2O, it acts as an arrhenius base also. So aliphatic amines or primary, secondary, tertiary amine and ammonia are Lewis bases. It is also a arrhenius base. Ultimate responsibility is because of the lone pair of electron, right? It's because only of the lone pair of electron that H plus has been abstracted and OH minus has been produced, and that is why it is acting as base. So it is acting as basic compound because of the lone pair of electron. It is a Lewis base because it donates the pair of electron. It is an Arrhenius base because when dissolved in water it produces OH minus. So that is the basicity of amines. I think this concept is clear. Now what we have to do, we have to look the basicity of these, okay, primary, secondary and tertiary amine, and then we have to compare the basicities of primary with secondary and tertiary. So how to calculate basicity? Okay, that is the question that is there before us. So I am going to rub everything here except primary amine, except the reaction of primary amine. I want to calculate the basicity or the strength as a base, the strength of this base. How will I calculate the strength of this base? It will be the extent of dissociation divided by the reactant that was used. How is the strength of the base calculated? The extent of dissociation, how much has been dissociated divided by how much was used. So the equation would be like this, right? The products, the dissociation product and how much was used, the reactants, right? Now this is the equation. Now this is a constant value. This value will be constant because this value is dependent upon the nature of the amine. So this value is always constant. The extent of dissociation in water is always constant because that depends upon the nature of this, the basic nature, basicity nature of this substrate. So this constant I will give the name as base dissociation constant or Kb. It is always constant. Now H2O is very large in quantity, right? Its concentration is very high. Only some amount of H2O is reacting. That amount is actually negligible because considering that the H2O used is having a very high concentration, this amount of H2O, that is reacted amount of H2O, is very negligible. So this is actually a constant value, right? It doesn't have any effect on the Kb. So we can rub it. So now the equation becomes like this, right? So in this way we can calculate our base dissociation constant for primary, secondary and tertiary amine, right? So we have calculated it, and the result of calculation I am going to write. The result is as this: Kb for ammonia, base dissociation constant for ammonia is 0.2 into 10 raised to the power minus 4. Kb for primary amine, that is methylamine, it is 4.2 into 10 raised to the power minus 4. Kb for dimethylamine, CH3 twice NH2 dimethylamine, dissociation constant is 6.0 into 10 raised to the power minus 4. Kb for trimethylamine, I am going to write this like this, it's one and the same thing, right? Kb for trimethylamine is how much? It is 0.6 into 10 raised to the power minus 4. So by the equation that I have given earlier, we have calculated Kb's for these. The Kb's are already set, it is a constant value, no need to calculate, it is already given that this is the value of the base dissociation constant. Okay, so this is the extent of dissociation. Now which is the most highest value, which is the strongest base? So as evident from here, this dimethylamine, that is the strongest base. That is, dimethylamine is secondary amine, that is the strongest of all bases. This is followed by methylamine. So number 2 methylamine. That is primary amine is number 2 position. And number 3rd position who will get? Yes, the tertiary amine is number 3 position in basicity. And lastly, the least of all basic is ammonia. So I am going to write it order wise. Let me write it order wise what we have discussed. Which is the most basic? Which is the most basic? Yes. Which one? Right. I'm going to write it here. The most basic, accordingly what we have found out, the most basic is secondary amine. After that followed by primary amine. This is followed by tertiary amine. And last ammonia. So the basicity increases in this order. Right? Basicity increases. Now we will discuss, we will prove why secondary amine is the most basic of all amines. What we will prove? We will prove why secondary amine is the most basic of all the amines, and also we will compare the basicity of secondary with primary and primary with tertiary amine and also with ammonia. Let us now go to the third part of this video, that is we will reason out. Okay, we will give reason for the basicity of secondary amine. So for this there are two types of reasoning. Number 1, first type of reasoning is based on balance between 3 effects. Okay, based on balance between 3 effects. Number 1, electronic effect. Number 2, steric effect. And number 3, solvation effect. So based on these 3, we can say, we will prove that secondary amine is the most basic. So first we will discuss about the electronic and the steric effect. Okay, and then we will discuss about solvating effect. That would be more comfortable for us to understand. Okay, so first we will discuss about the electronic and steric effect and how these effects play a role in greatly increasing the basicity of the secondary amine. So let us see. Based on the balance between the 3 effects. Okay, so let us first see the structure of amine. Primary amine, this is the primary amine, right? Now if you see an electron with pumping group, alkyl group is directly attached to nitrogen. It will pump its electron to nitrogen. So the electron cloud of this group, that is alkyl group, will be somewhat shifted to nitrogen atom. So that would increase the electron density around nitrogen atom, and that would cause higher availability of the lone pair of electron. Okay, so this would be more basic compared to ammonia, where there is no R group. Okay, so here because R group, it is an electron pumping group, it donates its electron or it shifts its electron cloud towards N, and that increases the electron density around N, that increases the availability of the lone pair of electron here, and that is what makes it more basic compared to ammonia, where there is no electron pumping group. On the same line of argument, look at your secondary amine. Now there are 2 pumping groups, so they can pump their electron to nitrogen. So the electron density around nitrogen will be greatly increased, more than this, right? And the availability of the lone pair of electron will also be more increased. It will be relatively much more increased compared to primary amine. So this will be more basic than primary amine. Now let us go for tertiary amine. This is tertiary amine. According to our line of argument, what we are saying, more the number of R groups, more the pumping effect would be. So there are 3 R groups, there will be more pumping. So there will be higher electron density around nitrogen atom. This should increase the availability of lone pair of electron. This actually increases the availability of the lone pair of electron, no doubt about it. But there is steric hindrance here, steric hindrance owing to bulky R groups. There is a big steric hindrance here owing to bulky R groups. With the result, the proton never finds its way towards the nitrogen atom. Okay, it blocks the path. It's not like this. It blocks the path of towards nitrogen. So here, in case of tertiary amine, the steric effect predominates the electronic effect. I already told you that there is a balance, right? Here the steric effect is more and it predominates over the electronic effect. Actually what we are trying to say is that more alkyl group, more will be the pumping. Here there are 3 alkyl groups, so pumping will be more. So more electron will be, density will be around nitrogen atom. This will increase the availability of lone pair of electron, definitely. And because of that, the tertiary amine should be more basic, but however, due to steric hindrance of the 3R group, the proton never finds its way to nitrogen atom, right? So here the steric hindrance predominates, the steric effect predominates the electronic effect. Here steric effect does not predominate. The electronic effect predominates the steric effect. Here of course the electronic effect predominates steric effect, and that is why it is basic. So here it is most ideal, right, where the electronic effect is very high. So and the steric effect becomes comparatively weaker. So using this line of argument, we find that secondary amine is the most basic among these 3. This will be followed by primary amine, right, and that will be followed by tertiary amine, right? Tertiary amine actually is basic, but because of the steric effect it is not, right? So this is the line of this is the argument where balance between steric and electronic effects have been highlighted. Now let us come to solvation effects. Balance between solvation, steric as well as electronic effect. Let us see the solvation effect also. Now if H plus is formed, for example your primary aliphatic amine, right, this is the primary aliphatic amine, on abstraction of proton from water, what is formed? What is formed? Alkyl ammonium ion. This is what is formed for primary amine. What about secondary amine? What is formed? This is what is formed for secondary amine, right? For tertiary amine, what is formed? This is what is formed, trialkyl ammonium ion. This is what is formed when H plus is subtracted from water. This is formed for primary amine, this is formed for secondary amine, this is formed for tertiary amine. Now solvation effect means that it is dissolved in water, right, and it can form hydrogen bonds with water. How? This is water. Water is polar, okay, and now nitrogen, there will be attraction here. It will try to take electron from hydrogen, so there will be some decrease of positive charge here. Okay, there is a pulling here also, because this is also electronegative. Of course this will not pull from here because both are electronegative. So there is a pulling from this end, from the hydrogen. So that interaction will be a hydrogen bond interaction. A hydrogen bonding will be formed and sufficient solvation will occur because of such a hydrogen bond interaction from all sides in case of your primary amine. In case of primary amine. In case of secondary amine also, interaction is possible from all sites except from these sites, right? Except from these sites, interaction is possible with water. Hydrogen bond interactions are possible like this. In case of your tertiary amine, this much interaction is not possible because here there are big bulky groups, right? So that much interaction with this ion is not possible. So the magnitude of positive charge here, it does not decreases significantly, but here it decreases significantly. So here primary amine becomes the winner, correct? Because here the interaction with water molecule is possible from all the sites, and that would definitely decrease the positive charge here, correct? So that will increase the stability of the ammonium ion that is formed. So here the winner, of course, the the formation of this structure is favored. So here primary amine is seen as the winner, and the loser is the tertiary amine here. So tertiary amine loses here also. Here also its basicity is low. Its formation, the formation of such an anion by abstraction of proton is low here also. So here also the tertiary amine becomes a failure. Now the competition is between primary and secondary amine. Primary amine is absolutely the winner here, but the electronic effect of secondary amine, which is within the molecule, has a greater influence than the solvation effect from outside the molecule. Okay, the electronic effect, that is the plus I effect within the molecule, it has a greater influence than the solvation effect with the solvent molecules. So because of that, secondary amine, the positive charge here, it would much more decrease than for primary amine owing to hydrogen bond interaction. Because of the electronic effect, the positive charge in a secondary amine would be less than the decrease in positive charge of the primary aliphatic amine owing to hydrogen bond interaction with the solvent molecules. So because of this balance, the electronic effect here predominates, and therefore here also secondary amine is the winner. Dear students, we have proved that secondary amine is more basic, followed by primary amine, followed by tertiary amine, just by looking at the forces at play. Which are the three forces that are at play? The electronic effect is at play, the steric effect is at play, and on the other hand, solvation effect of water molecule is also in the play. And it is a balance between these forces that determines that ultimately decides that secondary amine should win as a base, or it should be the most basic. Now there is another way of debating this. There is another way of looking at this. Number two, another way of looking at this based on stability of ammonium ions. Let us look at the stability of ammonium ions and decide. So what ammonium ion will be formed? For ammonia, NH4 plus. For ammonia, if it reacts with water, NH4 plus will be formed, right? What will be formed for your primary amine? This will be formed for primary amine, that is alkyl ammonium ion. What will be formed for secondary amine? This will be formed for secondary amine. And for tertiary amine, what will be formed? This will be formed for tertiary amine. So these are the ammonium ions that is formed for primary, secondary and tertiary amine when H plus is subtracted from the water. Now let us see the stability of these molecules. Is this stable? No. Is there someone to decrease the positive charge? No. Is this stable? Yes, to some extent, because R gives its electron, R pumps its electron to nitrogen and decreases the positive charge to some extent. Is this stable? Let me draw here R. Yes, to a very good extent, right? Because R pumping group is pumping its electron from both the ends, and that decreases the positive sign on nitrogen atom. So it is its formation is favored. Now, is this favored? Absolutely yes, because R is from three sides. It is pumping from three sides, and that would significantly decrease the positive charge here. So in which of these cases the positive charge will be the most reduced? The positive charge will be the most reduced in which of these ions? Which of these ammonium ions the positive charge will be most reduced? Yes, in primary ammonia, in primary amine, the positive charge will be the most reduced. So here the winner seems to be primary aliphatic amine, right? Here the winner seems to be primary aliphatic amine. That means primary aliphatic amine should dissociate more because the formation of this is more favored. However, for the formation of this ion, H has to enter, right? H has to enter, but H is never entering owing to steric hindrances from the three ends. So H has never been able to enter here to form such an ion because of the steric hindrance. So here also, because the first step has not taken place, why should we talk about the second step, right? That is the second step. When H comes, it would be favorable, but there is no chance of H of proton attacking this owing to the steric hindrance. So here also the the tertiary amine loses. Here also tertiary amine loses, and the ultimate winner here also is the secondary amine, because this is possible. H can enter. Here also it is possible, but its formation is much favored because it is more, its positive charge is greatly reduced and it is more stable, so its formation is favored. So secondary amine also wins if you are seeing it with the on the perspective of stability of the ammonium ion. Dear students, that is what is stability. That is how we prove that secondary amine is the most basic, and followed by primary amine, followed by tertiary amine, and the least basic of all is ammonia. Now let us discuss the effect of substituents in the basicity of amine. This is very simple. Suppose an electron donating group is present, what would happen? Yes, it would of course increase the availability of the lone pair of electron, and that would result in amines becoming more basic, right? And if an electron withdrawing group, if it is present, what would happen? Yes, that would decrease the availability of electrons in nitrogen, and because of this it would be less basic. Examples of electron donating groups are alkyl groups, right? These are alkyl groups. There are other groups also which can donate your electrons. Examples of electron withdrawing groups are COH, right? CHO, right? Ester groups, and here you can write OH group also, right? So if whenever an electron withdrawing group such as a chlorine or a fluorine group is present, it withdraws the electron, that decreases the availability of the lone pair of electron, making this less basic. And if an electron donating group like an alkyl group or any OH group, if it is present here, what would happen? It would increase the availability of electron, that would make it more basic. So that is the effect of substituents on the basicity of amine. Dear students, we have seen that amines are basic in nature, and now we know why they are basic in nature. All because they have got a lone pair of electron. It all started from a lone pair of electron. We have also seen that secondary amines are the most basic. All effects are actually favoring secondary amine, especially the electronic effect. It is the electronic effect that was able to negate steric effect and solvation effect in the case of secondary amines, and that is why secondary amines was most basic. Lastly, we have seen the effect of substituents and how electron donating groups increase the basicity of amine. Dear students, if you have liked the class, if you have understood it, please do not forget to subscribe the channel. Thank you very much.